Hi, I'm David with General Air. Having your MIG welder set properly will lead to the best welds that you can make. Set improperly, well, they can lead to some frustration. Today we're going to talk about wire feed speed, voltage, and contact tip to work distance, how to adjust them, and how do we know that they're set correctly. The first and most important setting that you need to think about is wire feed speed. And it sounds exactly like it is. It's the rate at which the wire is coming out of the gun. The more wire feed speed that you have, the more amperage that you produce in your weld. The more amperage you produce, the more penetration that you get in the weld, or the more punch into your material. If your wire feed speed is set too high for the material thickness that you're on, well, then the wire just blows right through the plate. If it's not set high enough, then you'll have lack of fusion, or where the weld doesn't punch enough into the plate and we don't get a strong or structural weld. Now, in either of these scenarios, it would really depend on the thickness of the material that we're welding. So if you're welding thin gauge material, then you want a low wire feed speed. A thick gauge material, you want a high wire feed speed. And also wire feed speed makes sense because the more wire that you're dumping out of the gun, the larger the weld that you're going to make. And if we're on thicker material, of course, we want a bit larger weld there. If we're on thinner material, we want a thinner weld, and that makes sense. So where do we start between 50 and 800? Where's the sweet spot there? This is where the charts on the machine come in handy. So typically on the inside of the machine or on this machine, there's a little flip out panel and it tells you if you're running 035 wire and 1/4 inch thick material, here's where a good place to start on your wire feed speed is. Now, the thing is, it's not always perfect. We need to have the ability to recognize when it's too high. So we're gonna set this machine up 240 inches per minute, and that's where our chart said it's a good place to go for our 1/8 inch material. We're gonna make a couple of different welds and talk about why this may not be the correct setting. The wire feed speed on our machine is set at 240 inches per minute. This is a great wire feed speed for how the material is configured right here. It's nice and flat, gravity's helping us out, and it's sitting on a table, which is gonna act like a heat sink. It's gonna pull all the heat out of our weld. So I'm gonna make this weld, and we're gonna take a look at it, and then we'll set it up in a scenario where this wire feed speed is not optimal. The last weld we did was a lap joint. You saw that and how those settings that we had were great, and they would work well for a T-joint as well. Anything where the corners are touching. But now I have corners that are open, so there's an air gap in between. This is where my 240 inches per minute is not really gonna work all that well. Even though we're using the same exact material thickness, same wire, same gas, everything's gonna be the same except for the configuration of the material. So since they're not touching and there's a gap, we actually have to turn the wire feed speed down. And the reason that is because edges are more vulnerable to heat than the bellies of the plates or the middles of the plates. And since the two parent metals aren't touching, they're both going to have to brunt the heat load individually, and this could cause us to blow through. I'm going to leave the settings at 240 on the wire feed speed. I'm going to try to weld this, and we'll see what happens. And there it is, you can see it, 240 inches per minute, which was fine on our other weld, but here it blew through only after about 1 inch of weld. You can really see that material start to sink down lower into the plate. This is how I know as a welder I need to turn my wire feed speed down when I really start to see this weld get out of control. And then over here, as we got closer to the edge, it just blew through, and we can flip it over and see, ooh man, got way too much penetration in there. There's a lot of material on the back side of the plate. So I've got to turn the machine down. Well, where do I turn it down now? Well, I could look on that chart and I can find the parameters for a thinner piece of metal. So I could put my machine at, say, like the 14 or the 16 gauge. And then I would want to test this out. Just grab a little tester piece and then just see if the settings are good, especially if I have a pretty big gap in there. So what I'm going to do is I'm going to turn my machine settings down to something maybe more appropriate for 16 gauge, and then we'll see if it works. So that was 130 inches per minute. So you can tell from 240 to 130, well, got less penetration and we didn't dump as much wire in there and didn't come as close to blowing through as we did there, but it's still, the leading edge of the puddle was a little unstable. There's a few times I had to work backwards to save it from popping through. And if we look on the underside here, you can see, yeah, it popped through one time and there's quite a lot of penetration there. So even still, I'm going to turn the machine down further to get a better looking weld here. $130, 100, and now I'm starting to get the results that I want. I really don't need a lot of penetration here because there's already an open root. There's a gap in between the material. So if we flip it over here, we can see it got plenty of penetration on the backside. What I just don't want to do is blow through or just put any amount of excessive heat into the plate unnecessarily. So this proves that wire feed speed is penetration. If I leave it at that higher wire feed speed number, it's just going to keep pushing through. And if I'm on edges or sensitive parts of my material, so like corners and places where the material thins out, then I want to go down with that wire feed speed. Now I know that some of your machines don't have digital gauges. They don't tell you exactly the wire feed speed to be on, but that's okay. You can still keep this theory in mind, because if your machine says like ABCD for wire feed speed or 0 through 100 or whatever it may say, when you flip it over or flip the lid and look at the chart, you can see that it's going to suggest a certain wire feed speed for a certain thickness of material, but now you know, hey, it really depends on how that material is configured. Now that we have our wire feed speed figured out and what that does in the weld, the next setting is our voltage. Now welders commonly refer to voltage as heat, but the big thing is it's not really heat. Wire feed speed equals the heat or the penetration in the weld. If you're blowing through the plate, it's probably not the fault of voltage. Let's talk about what voltage actually does. So if I turn on my flashlight here, and we're going to pretend for a second that the tip of my flashlight is the tip of the wire. As we turn our voltage down, the arc gets more concentrated on our material. As we turn our voltage up, then the arc starts to spread out. So as I push my flashlight in, light gets more focused. As I pull it out, the light starts to get more spread out. And this is exactly what voltage does in the arc. If our voltage is too low and our arc length is too small, it can't fit all the wire that the machine is trying to feed out inside that arc, and it's going to cause our bead to be very convex or humped up, and it's going to cause the gun to stub in your hand. It's going to cause all sorts of racket in the weld. The weld is just not going to sound, it's not going to sound like what it should sound like. Okay, we want a nice smooth sound, and this is going to be all interrupted. As we turn the voltage up, what you'll see is that the arc length will get taller, and in our hoods, the arc will actually get brighter as well. And what that does is it relaxes the arc, and now we can fit all the wire that we're trying to feed out into the puddle. Now we can take this too far as well. If we turn the voltage up too high, now our arc length's too long, and then the little droplets of metal that are coming off of our wire have to take a really long path through the arc to get into the puddle, and they can usually, or what usually happens is they spit out of the side, causing a lot of spatter issues. Now, just like with wire feed speed, voltage can be controlled down from 10 volts on this machine all the way to 45 volts on this machine and anywhere in between. So the question becomes, well, where do I even put it? Do you start at 10 and then just keep incrementally going up? Well, no, the chart can tell you also, hey, if you're welding that 035 wire, the 1/8 inch mild steel, and here's your wire feed speed, and here's a complementary voltage that you can use. And again, typically the chart is a good place to start. But I'll show you a couple scenarios here where using the voltage on the chart may not be the best thing for what we want to do. The more we understand about the machine, the better we can control it. When your voltage is too low, like we saw with the flashlight example, our arc length and the focus of the arc is going to be way too tight. So my wire feed speed is, I'm just going to leave it at 240 inches per minute, so I'm not even going to touch that, but my voltage, I'm going to play around. So right now the voltage is at 10. If we were to look at the chart and what the chart wants us to do, it wants us to be at 18. So let's see what happens when our arc length is too small and it can't fit all the wire we're going to try to dump out into the weld. Let's see what happens. So right off the bat, what I heard is the arc was just not very stable. It was popping and cracking, and it just wasn't very smooth. Now, I felt with the gun was stubbing back and forth, and that's because that arc length, again, was way too small, way too focused, and you can see what it did to the bead. You can see how convex this bead is. Now, when we turn the voltage up and we relax the bead, then this bead's basically going to sit really nice and flush against the material. And that's why a lot of people say that voltage is heat. Now again, it's not about that. It's basically how much room or how wide the arc is at its base. Now this weld is definitely not strong at all. Probably a good hit with a hammer and the weld would just simply pop right off. So let's turn the voltage up and see what happens. All right, 10 volts and 24 volts. Now, there's pluses and minuses of both welds. Well, actually, there's no pluses to the too low voltage. That weld's horrible and that won't stand the test of time. But the higher voltage weld, there's only a few little problems with this one. First off, we'll talk about the spatter. And that's the pieces of the wire that didn't quite make it into the weld and got thrown out of the way. This happens because our arc length is really, really long. So the pieces of wire have to travel a really long way through the arc, and sometimes they just get shot out of the side. Now, this is not the biggest deal in the world. It's just more cleanup you have to do in the end. But the thing that I don't really like is all of the soot on the weld. You can see this soot here, and what that is caused by is this spatter flying through the arc and creating turbulence, and then it starts to suck in atmosphere, namely nitrogen. And I know that when nitrogen gets into our liquid metal, we get iron nitride, which can make the weld brittle, and of course we don't really want that. The other problem with our voltage being too high is sometimes the arc path or the width of the arc is wider than what the wire can actually fill in, and we tend to get undercut, especially on the upper toe here in this region. And you can tell that by taking a little scraper and going back and forth. If it's not smooth, like there's a little valley there, that's a place where you could have a stress riser and a premature failure. So there is a optimal voltage for the wire feed speed that we're on, and remember at 240 inches per minute, the chart would say 18 volts, but we wouldn't be wrong at 17 volts or 16 volts or 19 volts or 20 volts. We can go up or down a few volts and that's fine. What it really controls is the bead profile. So if you make a weld and it's really convex, try turning your voltage up little bits at a time, only a half a volt at a time, until you start to see your bead lay down flatter. Now we've got wire feed speed and voltage knocked out. We're starting to understand what those do. But in the beginning of the video, I'd mentioned contact tip to work distance. So what is that? Well, that's the distance between the face of the contact tip and our work. And when we're welding with short circuit transfer, it really matters the distance in between here and here. If we looked on our chart again, it would say, hey, I want it to be within 1/4 to 1/2 of an inch. If we start to get out any longer than that and we start to pull the gun away, one, we'll start to lose gas coverage, which is a bad thing. We don't want atmosphere in our weld. But two, our electrons have to go from this plate to the contact tip, and they jump through the arc and then they ride up this wire into the contact tip. And the longer that this wire is, the more resistance there is on the electrons trying to go from here to here. and that causes our amperage to actually drop, and we know if our amperage drops, we get less punch in our material and make a bad weld. So we want to keep our contact tip to work distance as consistent as possible, and it needs to be 1/4 to 1/2 of an inch away. I'm going to start off our weld. We've got good welding procedures here. I'm going to start off our weld at 1/4 of an inch contact tip to work distance, and then I'm going to back the gun out till I'm at 1 inch contact tip to work distance so we can see the difference between the two. Take a look at the weld. It was started off pretty nice, and then I started to back the gun away, and then it started to lose amperage. So it started to lose punch in the material. And then about right here, right there, and right there, there's these little pinholes, and that's porosity. That's where the gas couldn't keep up, and we started to get the atmosphere sucked in there. That's not a good weld at all. There's iron nitrides in there, so we want to grind that completely out. We can't just weld back over that. So we've got to control that contact tip to work distance. It is a critical parameter. With the right settings on your MIG machine, it'll make any weld possible. Thank you so much for watching. If you like our channel, please subscribe so you don't miss any of our videos. Travel speed. That's how fast you as the welder go from point A to point B. Now we can get this wrong. You could have perfect wire feed speed, perfect voltage, perfect contact tip to work distance, but if you're going too slow or too fast, it'll either cause one of these two problems. One, you'll put too much heat into the plate by moving too slow, or you won't put enough heat into the plate by moving too fast. On the right side of the plate, I'm gonna move way too slow, and then on the left side of the plate, I'm gonna move way too fast, and we'll look at the difference. Here's too slow, and here's too fast. And there's a problem with both of them. Let's look at too slow. This one I made big giant circles and hung out for a really long time. So I dumped too much heat into this plate and I've got this big heat affected zone. So I've got some unintentional warpage, and worse yet, I could have annealed the plate. That means outside of the weld in what's called the heat affected zone, I could have a weak spot. So the weld's not gonna fail, but the plate might prematurely fail. On this side, the weld is too fast. What we want is we want an 1/8 inch weld. So I want to go from the root of the weld or the center of the two pieces up an 1/8 and out an 1/8. And you can see that it didn't quite get all the way to the top of the plate there. And in the right scenario, this one would fail prematurely, probably break right in the middle or maybe right there in the toe of the weld. So you got to work on your travel speed. What I do is I watch the toes, and that's the outer edges here. And as long as they're staying symmetrical, and I'm just judging that by watching the liquid puddle, then you know you're gonna make a good size weld. If you're going too slow, then you'll start to see that puddle start getting bigger and bigger and bigger. Well, you know that you need to speed up. On the other hand, if the weld is wiggling in and out and the toes of the weld are changing constantly, it's like it's trying to keep up with your arc, you know you're going too fast. Thank you so much for watching. If you like our channel, please subscribe so you don't miss any of our videos.